So I was asked to do this talk as I was coined heritage speaker or something like that, which is extremely impressive and feel honored. And I'll try to stay faithful to that mission. And the way I understood that, so this conference is a sequel, or comes after a conference that Serge Cantat had set up in 2006 in Rennes. Many things make this conference different from the previous one. First, I had talked in French. Second, my hair is slightly more gray because it was 18 years ago. And also, I've basically done something else than algebraic dynamics in between. Except that sometimes miracles happen. So I wondered what I could say for this conference. I was not keen to talk about my own work. And so Charles said to me, well, maybe you can talk about this Yuan Zhang stuff. And I said, well, I've not read it, so that's a good opportunity to read it. And so I tried to present you so the title is something like Intersection Theory and Heights. And then with a subtitle, just to be fancy, birational perspective. But, and so it's but I view this talk as a bridge between the previous conference and this one. So I'll first start by recapping the contents of my lectures in Rennes in 2018. Well, it would be quick and nice, but in Rennes, my lectures were devoted to equidistribution theorems for dynamical systems of arithmetic origin, algebraic arithmetic. So we had a variety, projective variety over a number field. And maybe say Q and a self-map. A finite map, and in all these theories there is some kind of polarization. So L will be an ample line model on X with some which is fixed point in the Picard group. So the prominent example so the first one is just take X is P1, and F will be a rational function, so in one variable of degree Q greater than 1. And the line model, you just take the tautological line model that you know on P1. You can also have this on many variables, so Pn, and then F will be given by n plus 1 forms in n plus 1 variables without common zeros. And the homogeneous of degree Q, and without common zeros, except the origin if you view it in this setting. And if you want a fancier examples, at least for me, who comes from number theory, algebraic geometry, take an abelian variety. And f could be multiplication by 2. This example from a dynamical perspective is not as interesting as the previous one, but for people who come from number theory, it's more striking. So I was supposed to use the motor, but as you see. So in this context, there is a notion of height. Which will be a function. I will index it by L, but it's not so important, from the algebraic point of x to the real number. And the notion of height goes back to André Weil, and is not well defined in the classical setting of algebraic geometry. By not well defined means that there are various normalizations that you can choose, and you don't have an actual function, but a function only well-defined modulo addition of a bounded function. But this function measures at least the arithmetic complexity of points. And for example, I just say that on P1, if you take a point x which has two homogeneous coordinates a and b are integers and co-prime, then the height is just the log of the maximum of a and b. So if it's, then you have other examples to give, but that's okay. So this function here, it's, you have one instance where it's not well defined, in my sense. I mean, if you change the homogeneous coordinates, it changes slightly the function, but not too much. But in the framework of dynamical systems, there is a canonical normalization of the height, which is and I think for dynamical systems, the name to quote is Joseph Silverman, and the inspiration comes from Tate in the case of abelian varieties. So it would be still a function on the real numbers, on x of q bar with valued in the real numbers, but then it satisfied the fact that the height of iterate is just q times the height of x. And so let's say, just say this. So the interest of this function with respect to dynamics is that this height function allows you to detect some points. So pre-periodic points with respect to f correspond exactly to the point of height 0. And this is due to the fact that I did not recall here, that there is a finiteness theorem for example, over the ground field, over Q, say you have finitely many points of given height, I mean, height bounded by something. And you can see it here, because if you bound this, you bound A and B, so you have finitely many integers. And the general result is that over an extension of bounded degree, you have finitely many points of bounded height. And now, if you take a pre-periodic point, it will be the case that f n plus m of x is, say, fn of x, and m is greater or equal than 1. And then the equation tells you that just q n plus m height of x is q n height of x. So you get that the height is 0. And in the other way around, if the height is 0, then the family of iterates, the points of all have height 0. And because of the finiteness theorem, there must be finitely many iterates, so you get a pre-periodic point. So, and the last thing, so maybe, so there are 3 blackboards, okay. So now let's learn how to use that. And so the last topic of the talk in Rennes was equidistribution theorems in this context. I think which go back to Spiro, Ilmo and Zhang in Arakelov geometry, but I think one should quote Yuan to get the generality. So is that if xn is a sequence of points in x of q bar, such that satisfying 2 conditions. So the first one, I say that the height, the normalized height, tend to 0. And the second is that the sequence is generic. So no infinite subsequence lies in a given strict subvariety. So then you can take the probability measure supported by the Galois orbit of xn, so you divide by cardinality of this orbit. So the Galois orbit, there is a fixed number field which was not even denoted on the blackboard, but say you have a point which is in q bar, so you take all the conjugates with respect to the fixed number field, and that gives you a cloud of points, and you just put 1 at each point, and then you divide by the number of points, so you get probability measures. And this converges to some canonical say equilibrium measure on x of c. What did I wish to say about this measure? So for example, so let's call it mu f. And so one way to define mu f, and people in dynamical systems have better intuition about it, but you could take the limit. You start from a Kähler form on x of c, you take the maximal power, and then you pull it back by f m times, and then you divide by, it should be q to the gm, and you make m go to infinity. Something like that. So you start from any measure, but then you just renormalize it along f, and you get something that, in a dynamical perspective, is very important, but for the moment, it's just that. Okay, so that was basically what I explained, except that it was on specific examples, especially in P1. But, so,
sorry, what's D here?
D is supposed to be, sorry. So D is a dimension of X. And, well, dimension in my talk is sometimes D, sometimes N. And sorry? Yeah, exactly. You want a probability measure. I should say something more anyway still. Let's put this up. That's a canonical brush. Well, no. So I want a few stuff between the relation between this canonical measure and the normalization of the height function. So, in classical presentation of height function, it's usually presented as a decomposition into local height functions. And those local height functions will be that, and I assume that L is represented by a divisor D. And then the local height will be a function on x minus d. Let's say pretend I'm only over the real number or the complex numbers for the moment to the real number, and I will write it gd because it will be a green function. Or maybe gd, or and meaning that if fd is a local equation for d, then if I take gd of x plus log of absolute value of fd of x, this extends by continuity. And this function will be, in my framework, it's always continuous. When GD is infinity, this equation can be reframed as the fact that if you take the DDC operator to GD and you add the integration current on the divisor D, then you get a smooth form if you extend that, if you assume that it extends smoothly and not only continuous. But now, what I wanted to say is that while there are many choices of green functions that reflect the many possible choices for height functions, there is in this framework a canonical green function, which usually will be only continuous. So canonical choice for JD. So I've been quite silent about what line bundles and divisors mean, but there is one equation that I did not explicitly use for the moment, is that f upper star L is QL. So what f upper star L is QL means that if I take f upper star G, the divisor that represents line bundle L, I get something which is essentially QD, but plus the divisor of a rational function. On X. And maybe, and now the point is that you can get the GD hat to satisfy G hat composed with F is Q GD hat plus log something like that. So you have a representative, a green function GD, so it will be GD hat, which is just that. Maybe it's well, signs don't matter. It should be okay, but and one way to define this green function is just you take the iterates and you divide by so GD hat. You see, if you have this, well, no, it's okay. Let's say, okay, if you have one green function and you modify it by composite with F, then you get another green function, but there is this modification that reflects this stuff. So you just correct by this, and then you divide by Q. So the operator sends GD to GD compose F plus log of U, and you divide by Q, which is another green function. And the stuff is that it's still a green function for G, and you can prove that it converges locally, uniformly to the normalized green function. And in the measure perspective, these green functions are very nice because if the GD height is very nice because of that. Because if you start from a green function so that the curvature, the DDC of it is strictly positive, like it is your Euler form, then you see that all of these functions will have DDC positive. They will all be plurisubharmonic outside of G. And so you get a function, GD hat, which is a limit. We should change. So 3 equals, no, sorry. So JD hat is plurisubharmonic outside of D. Well, it's not defined on D. So and if you look at DDC, GD hat, you get a positive closed 1-1 current outside, well. And essentially, mu f is also the product of the product of this current in the sense of, let's say, Bedford, Taylor, maybe de Mailly. Sorry. Essentially because this stuff, these products, which are products of distribution, so they should not exist, but they exist, and their existence is done by combining limit arguments and clever use of the Stokes formula and positivity to. Okay. That still doesn't really explain the dynamical importance of μF, but anyway. So, okay. Now what are motivations for further generalization of all of this? So unfortunately, I wanted that everything fits on a blackboard, but so I see two different motivations, which they are related, and Yuan and Zhang do so. The first one is the equidistribution theorem was only for objects defined over a number field, like Q or Q bar. So assume you have something that defined with some transcendental numbers in your formulas, then you can want to play the same game. I mean, you can want to look at points and their Galois orbit. Maybe you can just take the cloud of all pre-periodic points of some given order, something like that, gives you a cloud. And you may want to know that it converges, the probability, corresponding probability measures converge to something, and to the same thing. And the theory doesn't allow you to say that. So if you go to dynamical systems, you can try to prove it for dynamical systems, but otherwise, and anyway, the general framework will give more examples which are not related to dynamical systems necessarily. So you may want to do that. So maybe I should write. So first motivation extends to, and fields of finite type over Q, it's something which should not frighten you, because it means that the field is generated by finitely many elements, and if you have a dynamical systems as above, for example, a projective space, then you have finitely many polynomials, finitely many coefficients, finitely many numbers appearing in the formula. So you have a finitely generated field over Q. And it's not something fancy. Even if you believe that you start from complex numbers, I mean, they generate something which is small. So, the second motivation is the behavior in families. How are we supposed to write behavior? I've seen in Toronto a sign on a pub. It was written, forever neighbors, never neighbors. So, here there is an incredibly long list of examples. At the time, it seems I won't be able to reach the end of the list before I end the talk, but maybe that's okay. So the first example is take a family of abelian varieties, or of elliptic curves, if you wish. And maybe it's not over the full curve, but an up-at some set, and non-empty, of course, of a curve. See. And maybe you can take a dynamical system if you wish. But then assume that you have a point, but a family of points. I mean, so a section P of this projection. And this section will give you a point P, which in fact, or maybe could write like this, which belong to the maybe Q, maybe the over Q. So I get a geometric point over the function field of a curve. And also, whenever I have a point T in Q, in C of Q, or maybe C naught of Q, or Q bar, I will get a variety AT over Q bar, and a point PT in FT of Q bar, just because of the specialization of this point above this T. And there is a beautiful theorem of Joseph Silverman. So I want to take the one. No, sorry. It's the two. No, the three. Okay. Okay.
We did it until the end of the week.
I'm sorry.
Don't care about the others.
No, I'm sorry.
Thank you.
I try to control my strength next time. And so in this framework above, I don't know if you can read there. In this framework, we have the height, the geometric height of P, which is defined along the same lines of my earlier discussion, but over the function field of a curve. I could say H geom of P, and there are the arithmetic heights of the point PT. And the theorem is that with unspecified normalization in my talk, but in written papers you have more precise information, is that you take the height of PT, so it should be canonical height. The canonical height of PT divided by the height of T. This converges to the geometric height of P. And you may wish to understand this theorem in a greater generality, and here the proof uses a lot of the specific machinery of elliptic families and so on. And so you may wish to understand it better, and you also may wish to understand better that height of, if you look at height of PT, it looks like H geom of P multiplied by H of T. But can one understand this equality or this proximate equality better? With more precision, the equality, the approximate equality. Of course.
What is that convergence with respect to? What is T going towards?
So the height of T has to go to infinity. And the point is, if you admit the full machinery of Arakelov geometry and so on, and you assume that everybody has good reduction over every possible place and whatever, then it's clear what happens. The problem is that it's not so clear in details, and in this case, there was a proof in the book of Zhang, number theory 3. There is a proof of that for abelian varieties and so on, but not a proof because it's a survey on something, so there are links to something that should be a proof. But, well, you have to do some hardcore algebraic geometry, Faltings-Chai, and so on, to understand what happens, and it's not really transparent, and it's not easy to generalize at all. And this is for abelian varieties. The problem is that you may find good models, good schemes, and so on that represent the situation, and you're tempted to try to do the same for dynamical systems, and then you know that it's hopeless. So that's a bad direction of study, except that the good models and so on are beautiful for themselves. I mean, so here I have to just quote names. So of course, this in the case of elliptic surfaces, at least, your work with Mathématiques gave better understanding on what happens. And I understand that now there are results for families of algebraic abelian varieties. I think one should quote Carney, but I don't know what happened with these papers. I mean, still remains as preprints for years. And I did not read them in detail, so maybe there are I don't know. I can't bet. So the other example was this 1, 2. It was 1. Okay. The other example is the case of the Faltings height of abelian varieties. So this Faltings height is a height function on the moduli space of abelian varieties, which is the stuff that parameterizes all possible abelian varieties with some, say, dimension and degree of polarization fixed to fix the ideas. And this is an open variety for the reason that there are degenerating families, and there are families that go to the boundary, if I may say, of this moduli space. And Faltings, in his 93 papers, where he proved the model conjecture and the take conjecture and the Shafarevich conjecture, introduced the Faltings height of abelian varieties. And the definition is not exactly looking in the same way. There is, at some point, there is some AG bar and line bundle on AG bar and blah, 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 but it starts from taking an abelian variety of a number field and you compute a number. And if you try to, when Faltings translate his definition of the Faltings height of a given abelian variety of a number field to what it means over the moduli space, it appears that his green functions have singularities at infinity. I mean, they have the logarithmic singularity that I've claimed there should be, of course, but there is a further singularity. And so that means that this height function does not fit in the standard framework of Arakelov geometry. So there were attempts to put this singular heights within Arakelov geometry, especially the work of Bost and Ulf-Kuhn, but they were restricted to curves and using ideas from pluripotential theory. And so, for example, Bost showed that you could do a lot of work using green functions that are in the first Sobolev space, or continuous with derivative L2. But still, there was no, he did some work in some direction, but not in that one. So you get something which is a which is a logarithm of the logarithmic. You get log. And I don't write, since I'm not writing it, I won't go further, but there is the same for families of hyperbolic curves. You have canonical green function, and at the boundary, they don't go, they don't behave correctly, and they have logarithmic singularities. Here, the names to quote are Wolpert and Kuhn. And maybe further, so here there are singularities. And also there are questions like Bogomolov in families and stuff like that. So now you have a family of abelian varieties and a subvariety, and you look at torsion points, but not in a fixed abelian varieties, but in various fibers, and you want to understand what happens and what can happen. This gives a further reason to generalize this stuff. So now 20 minutes to say what can happen, and I'll say only half of my talk. That's okay, because that's the easier one. So it was not the correct one. Yeah. Okay. I think I wanted to erase that one. That's okay. I mean, we are not on TV. We're not supposed to talk every second because maybe that leaves you some time to relax or finish writing the blackboard. So what are the possible solutions? So as I said, you can try to work with more singular objects. So here I write the name of Bost and Kuhn. And did I write? Yeah, maybe Freixas as well. So try to work, Gerard Freixas. So try to work with these singular objects, but it's not so easy. Especially, it's not easy to put those objects within the framework of Arakelov geometry. I mean, in the full stuff with heights. This can be okay for the complex side of the world, but for the non-Archimedean side of the world, of the picture, this looks clearly difficult. So around 2009, so 2006, I had defined the analogs of the equilibrium measure on the non-Archimedean side, so using Berkovich spaces. But for example, the pluripotential theory is not at all well developed over QP or QP bar. I mean, it looks complicated. Charles knows better than me on that. And analysis, it's tough to do analysis on Berkovich spaces. So what Yuan and Zhang do is try to do what Zhang had already done the first time. Is try to look at approximation. So if you go back to the Tate, Silverman, Zhang approach to canonical heights. It's essentially limiting arguments from well-behaved heights. And what Yuan and Zhang will do is exactly doing one step further in that direction. So don't try to look at complicated objects, but look at reasonable objects, and that converge in some sense to the complicated one, and try to see what can be saved just within the limiting process. And this is essentially the idea of their 260 pages book. I mean, so there is a clear idea to what to do, and the question at some point is how to do it. But if you stick clear to your project and you have their commitment and strength and technical capacity, then you can go. And so if you compare these two objects and you come from complex analysis, here you try to look at any PSH functions. And here you look at PSH functions that are continuous and limit of smooth PSH ones. And you only do analysis with the smooth ones. Of course, sometimes it's important to know what is transferred and what it's important to try to go further, but that's okay. And there was, I was supposed to give a birational perspective. So I'm going to do algebraic geometry on the second part of the blackboard. Here, you see we have curves which are, the curve C0 is quasi-projective. So we don't know really what will happen at the boundary of C for these norms. And here it's a curve, but you can imagine you have families parameterized by something, and you have many models to take into account. And so here there is a theory by Sokurov of b-divisors. Namely, you take X, which is a projective variety, and you will look at cycles. So we'll take the projective limit of all, say, classes of numerical cycles on all proper and birational models. Sorry? Excuse me? Well, they call it b-divisors, but K is anything. It's bizarre, but so let's say quote divisors. But it's okay for me. At the end, K is 1. But okay, you take this. So this object is, so it means that you take classes Cy, which is in nk of y. Here it's just classes from numerical equivalence. Of course, you can take classes for rational equivalence, and then you get closer to the non-Arakelov geometry of Bloch, Chile, and Soulet. And then you will ask that f p upper star cz is cy when you have z to y and to x. And you take classes that are compatible in this sense. So those objects are very mysterious because it's not clear what relations you have here. But within these spaces, there is an inductive limit. And here you will take classes, classes of the form Cz is p upper star Cy for some y. So there are classes that are defined at some point, and then above them, above that y, is just you take pullback of what you had. And this stuff is called the Cartier classes by Sokurov and on this space, it's quite easy to understand what happens, because it's just birational behavior of intersection theory. So here you understand, here you can multiply classes, you see. So here in some sense is it's a smooth, those are the singular objects, those are the smooth objects. But the smooth objects are not enough. So there is a theory that tries to be developed, is to pass to the limit from the inductive limit. And this is not what Yuan and Zhang do explicitly, but essentially this is what they do, at least for k equals 1. I mean, could be interesting to develop the theory. So, 10 minutes, okay.
So when you say limit, you're talking about what topology?
What?
What is the topology that
That's something I need to say before the talk ends.
Oh, okay.
Because otherwise. So, what do Yuan and Zhang do? They say, okay, we are forced to look at quasi-projective varieties and do intersection theory on them and Arakelov geometry on them, because they appear in nature. And it's hopeless to assume that everything will extend nicely to the projective case. So we have to get quasi-projective varieties, but of course, there is no intersection numbers for affine varieties. You can put the intersection points at infinity, so there has to be some projective stuff in between, and the idea of b-divisor is nice. I mean, you can say, okay, it's at least you start from something that lives on some model, on some projective variety, or over a field, or over the integers. And they want, in this framework, to have line models with divisors with green functions, or line models with metrics, depending on your philosophy. And they want to have measures, not anymore on the blackboard, but the measure, the C1 of G hat, the DDC GD hat, whose maximal power goes to the equilibrium measure, so they want to have those measures. And they want to have canonical objects in the case of dynamical systems. And they achieve to extend the major results of Arakelov geometry in this framework, namely the fundamental inequality by Zhang, that the height of the points generically is greater than the height of the variety. And they extend the theory of arithmetic volumes on arithmetic volumes from geometry, algebraic geometry or arithmetic geometry. So this is a theory due to Yuan, Chen, Moriwaki, and many others. And they extend the equidistribution theorem in some sense. And they end with their book, or their monograph, with an application to dynamical system and to equidistribution theory for PCF points, which I will not talk about, but probably you will. And I want to say something. So in this equidistribution theorem, when they are in general situation, there is some hypothesis at some point that something is non-degenerate. And they don't prove that. So the machine doesn't prove everything that you may wish to know. So at that point, if you look at how you check the hypothesis, then the proof is go to Gautier-Vigny and Gautier-Okuyama-Vigny. So just to say that we will develop as I develop a general theory, I will just give a hint of it in 5 minutes. And by no way will this theory prove everything you want. At some point, you have to do geometry and to understand geometry. Just to be clear. But in some sense, all limiting arguments are taken care of for free now, which is something. So I will just maybe. So I will just show you the case of divisors. I mean, want to do intersection theory, a bit of intersection theory on the maybe on the Sokurov b-divisors, but you want to go further than what Cave and Khovansky did by taking only the Cartier classes, and not as far as what Charles did by taking the other side. Because the other side is complicated, doesn't work in positive characteristic, I presume. Probably not, but not yet, I mean. And this extension is easy. So, this. And so let's take V. So, example of limit intersection theory. So you take V over field K, quasi-projective. Variety, and we take a compactification such that x minus v is a divisor. It's standard to, if you take any compactification, you can blow up the boundary and you will be reduced to this case. And maybe Cartier divisor. You want that it be defined by an equation. And maybe, what did I say? No, let's call it delta. And now we have objects that are divisors D inside V. It's funny that. And we have this inductive limit of, say, divisor of X for all models. But we take objects here. So that means that's objects that live at some level. And this is an analog of smooth objects, so we need to complete it. And so what they just do here, they just define what they call the boundary topology, which is defined by a pseudometric or pseudonorm, because it can be infinite, that's it. And it's just saying that if we fix, so maybe we have fixed, I should write this y, and so this stuff is fixed. We say that on y, the pseudonorm of a divisor, say, you don't need to, is just the infimum of all t, such that d is smaller than t delta, or pullback of delta if y lives over x with p, and minus t phi over star delta. So it can be infinite if there is no comparison of this form, but otherwise it's and this behaves like a norm, and you can take the completion. So this is still too big. This is still too big, but now in this completion, you can look at well-behaved objects, and the well-behaved objects are just limits of classes. So I should say here, D should be in Y. Or of such D for this boundary, which are F. So you have your object is represented by a family of Neff divisors on various levels, and with this boundary convergence. And if you start from that, so that defines a cone inside the completion. So this could be called div hat of x. This defines a cone. Maybe one should take coefficients or real coefficients, but I will not care here. So this gives a cone inside div hat of x, on which intersection extends by the intersection product, numerical extends by continuity. And that's it. I mean, and the proof that it extends by continuity is quite transparent. I mean, it's a bit, it's multilinear, so you have to assume that by induction of the number of singular objects in your product, but you do it nicely if you're familiar with Bedford-Taylor theory and stuff like that. And then every other step, I mean, the arithmetic case and so on, is a variation on that. Sometimes more complicated, the notation doesn't help, but okay. I think right time to end, so thank you.
Now it's on. You can hear me? Okay. Thank you, Antoine, for a wonderful talk. Is there a quick question?
The reproduction limit is over what exactly?
Over
So
all,
So you have to keep V intact, right?
over all y over x that goes to, over all model that dominates y. So you have all these g2. You take all models that dominate the fixed x.
But it doesn't have to be an isomorphism over V?
Yeah, it has.
Okay.
It's models. It's over models of this V. Well, you could. In fact, it doesn't have. There is a further stuff which works the same.
Yeah, but then you have difficulty to.
No. It's the same. I mean, when they do over the function field, they assume that there is some V at some point.
Were there any other questions?
So what's the motivation for the metric that we defined?
Okay, so I'll give the definition of a metric on what happens for green function in this context, and then you'll see the motivation. I presume you're okay with green functions? Oh, well, I have to presume something. So if you remember the beginning of the talk, green functions were defined, assumed to be uniform convergence everywhere. So now they will just, so for what about green functions for such a limit object? So I have divisors on model, and I want green function. So I just assume that GD is a smooth positive green function for G. And what is the topology now? Because I have a topology here, but I need a topology there. And so the topology is that the topology is just the supremum. It's not the uniform limit, because if you take the uniform limit, then you will have uniform convergence everywhere, and you lose the singularity. So you just take a supremum of GD, say minus GD prime, divide by G delta, by some G delta, which is fixed. So that means that on the open part, outside on V, you have locally uniform convergence. And at the boundary, that you lose uniform convergence, but it's controlled by the G delta. And of course, the remark I should have said is that if you change, you start from another delta, and in fact, there is a bounded distortion between the first delta and the second one. And so all those topologies are the same, and limit stuff is the same. And so now, well, something I wish to say is that, for example, on V, if you talk with green functions, you get a PSH green function on the open set, on V. And so you can look at the limit measure in the sense of Bedford-Taylor on the open set. But it's defined because Bedford-Taylor theory is local. So. But now this measure could be, it's a limit of measures of some volumes, the limit of measures of volume that converge to this stuff, and you need to know that there is nothing that escapes to infinity. And that's a theorem that is proved in the monograph by Yuan and Zhang in some with some complicated hypothesis that everything comes over a field and so on. But a recent paper by Guo gives a transparent proof, which is clear from the point of view of that the stuff at infinity looks like defined by an algebraic equation, and you know that algebraic sets are not pluripolar and are pluripolar, and so they carry no mass for this stuff. And then so that's nice cutoff, which is transparent from the theory point of view of pluripotential theory, explain why this happens. And so now you see that you have a theory of divisors, green functions, the measure theory works well, and then further steps are needed to go forward.
Okay, wonderful. So I think coffee is waiting for us outside, so let's thank Antoine again.
Thank you.